Good morning, good evening, good afternoon, wherever you may be joining us. My name is Mark Richardson with Vibrant Technology, and I welcome you to another MEscope webinar. Today, I'm joined by my father, Mark Richardson Sr., the founder and CEO of Vibrant Technology, as well as our Director of Engineering, Brian Schwartz. And topic for today is MEscope Modal, specifically impact testing. And if you've joined us over the past, few years now, we've been really focusing a lot on the video ODS stuff with our partner, Dan Ambray. And so this is a little bit of a change for us. And we've had a tremendous response to doing these modal webinars. So we're going to continue with these modal webinars into the next year. And we'll talk about some more of the classes that'll be coming up in January and later on into the springtime. Let's see here. Before we get going, let me just talk a little bit about what we got going on. We are recording this webinar, so if you do want to go back and review this, you will get a link to the recording in your inbox probably in a day or so. In addition, we will be uploading this to our YouTube channel, so we'll get that up online sometime early part of next week. And if you haven't been out to our YouTube page, I encourage you to go out there and you can view all of our past webinars. There's recordings of everything on there. So many different webinars from over the years on various different topics. Another thing, during the webinar, everybody will be on mute. And if you do have questions, I encourage you to type your questions into the questions box there in the GoToWebinar panel on the right side of your screen. In addition, during the webinar, we're going to be doing a poll. So to try and make this a little bit interactive, we're going to pose a question out to the group and a simple yes or no answer. And based on that, I'm going to ask one or two of you to follow up with that, why you picked that answer. So the poll will go out here about midway through the webinar when we get to that slide, and we'll go from there. With that, I think I'm going to hand things over to you, Dad, and we can get going.
Okay, thank you, Mark, and welcome all of you. I can see the attendance is growing. Mark told me we had like 110 signups, and from my screen I can see 45 of you have shown up for this webinar, which is typical. We usually get about half of the signups who end up attending, which is good. But because of time changes and schedules and so forth, we certainly understand that many of you will probably look at the recording if you're interested. Today our topic is going to be impact testing. And I just want to go back because I've been in this business for many years. And that is modal analysis from the testing standpoint. I started in 1973 in Silicon Valley in Northern California when I took a job at Hewlett-Packard, which used to be an instrument company. Now it's a computer company. Back then, impact testing was a brand new technology. Prior to that, all of modal testing or modal analysis, experimental analysis, EMA, was done with shakers and sine waves. And that's still done today for the certainly the military and the industrial government testing labs worldwide still do a lot of testing with shakers and sine waves. But in 1968, I believe it was, two researchers at IBM wrote a paper on something called the FFT, the fast Fourier transform. So a number of instrument companies started implementing that algorithm in digital spectrum analyzers. And HP, when I hired on there, they already had an analyzer system that they sold to automotive and aerospace companies. During my interview, they said, they asked me, do you know anything about a mode of vibration? And luckily, I didn't have any experience with modal analysis, but one of my roommates in graduate school wrote his PhD thesis on the modes of a cantilever beam, the longitudinal modes. It was all analytical, but in helping him proofread his thesis, I knew a little bit about modes of vibration. So I got the job, and I began writing software very similar to MEscope. And so I've been doing the same thing for 50 years. Anyway, that's a little bit of the history of impact testing. Here's a graphic that was created back in the 70s at Hewlett-Packard that I used to use. It's still very valid today. But let's just go through this. Impact testing is the excitation of modes of a test article by applying a force with an impact hammer. So as opposed to a shaker in sinusoidal excitation, impacting is a different way to apply the force. What type of equipment is needed? A minimum of 2 acquisition channels, one to measure the force and digitize it, and the other one to digitize the accelerometer response. Now, there's other types of sensors that you can use, but we're just going to focus on the more traditional use of an impact hammer and an accelerometer for doing impact testing. Then there was something called a frequency response function, and it's defined as the digital frequency transform, DFT, of the accelerometer time waveform, TWF, divided by the DFT of the force, TWF. So that's what this picture shows. It shows a little beam here and a hammer that's impacting it. And on the head of the hammer is a load cell, which measures the compressive force. And then the accelerometer is mounted on the end of the beam, and it measures the acceleration of the beam due to the impact force. And you can see the TWFs and then the FFT algorithm, which is used to transform the sampled or digitized analog signals from those 2 sensors, the load cell and the accelerometer, into what we call time waveforms, or really just numbers in a computer. And those get transformed with the FFT, the fast Fourier transform, into different spectra. If you own a spectrum analyzer, I'm sure some of you do, then you might just look at the spectrum of a signal, and that's called an auto spectrum. If I use 2 signals and FFT them, I can form what's called a cross spectrum. And we have many other frequency domain measurements that we make from these digitized signals. But the FRF, the frequency response function, is the one that we use for extracting modal parameters from a set of experimental data. So there's 3 different parameters that we use to define a mode of vibration: frequency, damping, and a mode shape. And typically from an FRF, there'll be a number of them, and they're characterized by peaks. So a resonance peak in an FRF is due to a natural resonance or a mode of vibration of, in this case, the beam, or anything that's been had a force applied to it. So each of the peaks is an indication of a resonance, and we use curve fitting, and we're going to get into a lot more of that curve fitting in our next webinar, not today, how we extract the modal parameters, frequency, damping, and mode shape from a set of FRFs. Okay, so here, what causes a body to vibrate? Forces have to be applied to it. So from an engineering standpoint, even from a physics standpoint, the real world is pretty simple. When forces are applied to a body, or we often use the term structure. Isaac Newton wrote down a law many years ago. He was one of the fathers of the mathematics that we use to describe vibration, and it works surprisingly well in the real world. Anyway, F equals ma. The force applied to a body is equal to, it will cause it to accelerate. So it's equal to its mass times its acceleration. So that's what the formula F equals ma really means. So if I don't have any forces, nothing's going to vibrate. And the body has to have mass. So almost everything you can think of has mass, and it has elasticity. Now you can see the little picture here. The elasticity is represented by a spring. And we use different terms. A spring exerts a restoring force on the mass when a force is applied to it. And the restoring force is always opposite to the external force. So the force can be coming from all sorts of places. It can be multiple, distributed. As I mentioned, I started in this business in Silicon Valley back in the 70s. I was on my way to work in the late 80s, and the Loma Prieta earthquake struck in California. So those of us who live in California, I'm now speaking to you from Southern California, but we're used to earthquakes. And that's when a tremendous force, it's a shear force typically of the plates of the earth shearing with respect to one another. That force caused the ground in front of me, and I was on a highway going to work in San Jose, California. It caused it to vibrate, and it looked exactly like the beam here. When I looked out at the highway in front of me, I could see it deflecting with a shape to it, a waveform. And the car actually jumped right off the ground. The amplitude was so high from that resonance. Now that waveform was not trapped at what we call a continuous or infinite boundary condition. The energy was dispersed in the earth. And one thing about earthquakes is once the earth vibrates, about the time you get nervous about the vibration, it stops. So anyway, that's a mass with elasticity, and just about anything else that we can think of that we make things out of, cars, airplanes, machine tools, we make them out of metal, aluminum, steel, cast iron, plastic, epoxies, carbon fiber, you name it. Any of those materials, if we make something out of them, whatever we make is going to vibrate if forces are applied to it. So let me click on this little animation here from MEscope. This is the vibrant icon. You can see it down here in the lower right. All vibration can really be explained in terms of how this thing vibrates, a mass on a spring with a damper. All of the mechanisms that are involved in vibration can be explained by understanding the vibration of a mass on a spring. So you can see the damping force is this little dashpot thing here, and there'd typically be fluid in there. What does that remind you of? Well, the shock absorber on your car. And most modern cars actually have in the front end, at least with independent suspension of the wheels, the spring and the mass are all one unit because they both oppose the external force applied to the wheels of the car as you go over bumps and so forth. So whether the force is pushing or pulling on the mass of the car, the spring and the shock absorber, the dash pot, are opposing that vibration. So let's move on. Here's another one. So what causes the body to stop vibrating? Well, we all know that from experience. It's damping. So the dash pot, the damper, is going to cause anything that's vibrating to stop vibrating eventually when the forces are removed. So here's another animation of what we call an impulse response. So if I hit something, if I hit this mass with a hammer, it will begin to vibrate because it's got elasticity, but it's also got damping. So as time goes on, the damper is going to respond to the velocity of motion, and it's going to damp out the motion. So no matter how we excite the structure, the spring and the damper are going to resist the motion of the mass. And then the damper is eventually going to damp out the vibration. So there can be many mechanisms. I'll mention another one that's very common here on Earth, and that is the surrounding air. So anything that vibrates on the surface of the Earth and our atmosphere is surrounded by air, and it acts like a speaker in a sense that it's pushing the air around it as it vibrates, and the air is absorbing the energy. So it works exactly like a shock absorber. It's subject to the velocity of the body, the vibrating body, whatever it is. Okay, let's move on. What causes resonant vibration? Well, we've been talking about that. Here's another way to explain it, which I've always liked or prefer to use. The energy applied by the forces gets trapped within the boundaries of the structure or the body. And so what do you mean by boundaries? Well, that's a discontinuity between the material of the structure and its surroundings. So something underwater is going to have a discontinuity, like the hull of a submarine. The hull could vibrate, and the water around it is different, a different material. So there's a boundary there. Anyway, once the energy gets into the structure, it will move freely. It will deform freely within its boundaries. And the energy cannot readily escape. So how does it escape? Damping. The damping of the surroundings will eventually damp out the vibration. So striking a bell causes it to resonate. So resonant vibration is a natural property of any body that has mass and stiffness, or we use the terms back and forth, mass and elasticity. Striking a sandbag won't cause it to resonate. Now, how do we know when things are resonating or not? When we remove the force, like an impact force, the structure continues to vibrate. So when we ring a bell, the little clangor inside the bell, in this case, you can see a little picture of it, that causes an impact to the outside of the bell, the structure of the bell, and then when we kind of hold it still, it's no longer impacted, but it still rings, it still vibrates. Okay, so what is modal analysis? Like I say, when I interviewed for the first job in this business many years ago, they asked me, do you know anything about modal analysis? And luckily I knew a little bit and gave them, I guess, an intelligent answer, but here's the definition. It's the process of characterizing the dynamics of a machine or a mechanical structure in terms of its modes of vibration. So many of you are certainly familiar as engineers with finite element modeling. That is another way to characterize the vibration of a mechanical structure using just mathematics, just a computer model. We can solve that model for the modes of vibration. And of course, that's used heavily in industry now. Again, back when I started with the experimental modal analysis in the 70s, finite element analysis was still in its infancies. It was developed with a lot of funding from NASA for building models of the space vehicles, so we could go to the moon back in the 60s and 70s. Now that's grown up. That's a common tool. So we can compare answers from a computer model with the experimental data that we get. And what's the best way to do it? We can compare frequency, damping, and mode shape. Now there's a lot of limitations of the FEA model versus the experimental model and sources of error and so forth. We won't get into that today, but we just want to talk about resonant vibration because that's what modal analysis is all about. Defining the dynamics of a machine or mechanical structure in terms of its resonance. Okay, so here is a picture of a mode shape. Actually, a bunch of them. So what is a mode shape? It's a spatial deformation or spatial motion of resonant vibration at a particular frequency called its natural frequency. So over here in this spreadsheet, you can see that there's 5 modes of vibration. They each have a specific frequency that's called the natural frequency. They each have a value of damping associated with them. And that's due to the experimental damping, whatever damping mechanism was applied. In this case, it was a vibrating aluminum plate that we tested with impact testing. That's where this data came from. And the surrounding air certainly acted as the damping, let's say one of the damping mechanisms. Now there can be other damping going on inside the molecular structure of the material itself. Again, people research those kind of things down to the minute details. We won't get into that. Damping percent. This is a common term that's used to describe damping. And a heavily damped structure would be one where the percent is, let's say, greater than 1%. So one of the ways we want to suppress vibration is by adding more damping. The car industry is a good example. There's all sorts of dampers added to cars to suppress vibration. You can see that this damping is less than 1%. Percent being roughly being the amount of damping divided by the frequency. Now it's calculated a little differently, but that's a good way to think of it. Both the damping and frequency are in units of hertz. So frequency, no problem there, but damping also has units of hertz. So again, we won't get into all the details behind that, but these are just things to keep in mind when you're doing impact testing. Okay, spatial motion, the motion of 2 or more points. So if I just make one measurement on a structure, impact it and measure its response with one accelerometer located at one point, we can't say anything about the mode shape. We can say something about the frequency and the damping of that resonance from that one measurement, but we don't know what the mode shape is like. We can't make a picture like this until we have measured at least 2 or more points and directions. We call those degrees of freedom, DOF, on the vibrating structure. So another thing to keep in mind about resonant vibration is it's a mechanical amplifier, or it can be thought of as an amplifier. And that's why we want to know about resonances, because if a resonance gets excited by some external force, the response can be orders of magnitude greater than just the static deflection due to a static load. Now, statics is important in engineering also, because we don't want to put a load on a material that's beyond its elastic limit, because then it'll crack and fail. So we want to make sure that you know, whatever it is we're designing does not exceed its elastic limit. But if resonances get excited, then we can have premature material failure. So that's why it's important to understand, and in what we're talking about here today, modes of vibration. So a small dynamic load, if it's excited at the right place on the structure and at the right frequency, it can excite a resonance, which can cause it to break. Okay, so another way to characterize a mode of vibration, there's a lot of mathematics behind it. My son Mark made me promise not to use any math today, so other than F equals ma, we're not going to use any math. However, all of structural dynamics, vibration, modal analysis can be represented by differential equations, by integration, by differentiation. And the modes themselves are a mathematical representation of a structural resonance. And then again, there's three things: the frequency, the damping, the mode shape. Let's move on. Okay, there's something else, and we'll get into it a little later. We started this business with what we call an ODS package of MEscope. We didn't even have modal analysis in it. It was just an ODS package. And our video ODS, which is really called that, our options now to MEscope, and we have several of them, are again characterizing vibration in terms of an ODS. So what's an ODS? The acronym stands for Operational Deflection Shape. So it's similar to a mode shape. It's the motion or deformation of a body at 2 or more DOFs. So let me start this animation going over here. There is an ODS of the vibrant beam. Now that looks a whole lot like a mode shape. That one looks like what we would call second bending. And as we go up in frequency, you can see the cursor moving along in a set of data here. This is a frequency-based ODS. And a degree of freedom. So here's a definition of a DOF. It's motion at a point in a direction. So this model here, you can see the points are numbered. There's quite a few points where we tested the vibrant beam, impacted it with a hammer, and mounted an accelerometer on it to measure the vibration. And so those are ODSs, what are called frequency-based ODS. It's a function of frequency. It changes, and the amplitude changes, and the frequency changes. Now, there's no damping in an ODS. Let's go over here and look at a time-based ODS. Really a complicated looking deformation. And then in the video here, we're going to move the cursor along to a different sample in the impulse response. So these are just the inverse Fourier transform of the FRS on the left. That's an impulse response function. That's called an impulse response function. It's pretty much the same thing that we get from the accelerometer when we impact a test article like the vibrant beam with a hammer. So you can see it's very complicated, kind of hard to understand. However, embedded in that data are all the resonances of the beam because they're all getting excited. Let's move on. Here is what I've already alluded to. This is a time-based ODS. Again, deformation at a time sample. You can see the cursor moving along in those time records up there. Now there's actually thousands of them. Let's go back here and just start it. See if I can start it over again. Well, we'll let it run. It's down here looking at the frequency spectrum of the signal. Let's get it turned on here again. And these are extracted with something we call an optical flow algorithm. So it's kind of like curve fitting, only it's a little different. It processes the frames of a video, and we've been very successful processing frames of cell phone videos. Now this one is showing the motion which is the rotation of the fan blade. You can see a whole bunch of motion over here on the edge of the housing. And there's a screwdriver mounted here to suppress the vibration. So there's a lot of stuff going on in this picture that we can capture with a video that would be very difficult to capture with any other means. So this is something new to Vibrant and MEscope, the ability to use videos to acquire vibration of a machine. So here we got two types, a time-based ODS and an order-based ODS. So those peaks in the spectrum below are what we call orders. Those are multiples of the machine running speed. So in any running machine, even if it's well balanced, there are going to be cyclic forces due to the rotation of the machine, the rotating parts of the machine. Now in the time-based ODS, you can't see, well, you can see the overall vibration over there on the left-hand side. It's, you know, there's a lot of motion of this housing and so forth. When I go to the frequency-based or the order-based ODS, now I can actually see the resonant vibration or the deflection of the modes of the fan blade itself. So let's move on. What's the relationship between an ODS and mode shapes? An ODS is the summation of mode shapes. And all resonances are excited at all frequencies. So these are two fundamental properties of resonant vibration that we need to keep in mind. And when we make measurements with an accelerometer and impact hammer, we measure these FRFs, which we talked about, the ratio of the DFT of the accelerometer divided by the ratio of the divided by the DFT of the force. Now we calculate in other ways to get rid of noise and so forth, but that's the definition of an FRF. It's the response divided by the input. So with impact testing, it's the accelerometer divided by the force. And we get a curve like the blue curve. So you can see the blue curve's got 4 peaks in it. That's the magnitude of the FRF, or a log magnitude. It's on a log scale. But the important thing here, and again, this is a graphic from back in the 70s when I first started in this business. It's true of all resonant vibration, and it's what we apply in curve fitting FRF data. So we're not going to get into that today. However, this is a picture of how the overall data, and at any frequency, if I have 2 or more of these measurements, that's called an ODS. So this shows how the ODS is a summation of resonance curves, in this case, at all frequencies, due to each of the modes of vibration. So if I take the ODS at any frequency, and we saw the frequency-based ODS in the previous slides, it's a summation of mode shapes. So that's a critical piece of information. Let's just go back and review some of that. So here's just an ODS. These are ODSs. Now that certainly looks like what I would call a torsional mode, but well, that mode is dominating the ODS. There's one that I would call a bending mode, and again, second torsion. We give names to these ODSs. They're being dominated by the resonance. So the resonance is wrapped up in the ODS data. And what we measure from the structure by putting sensors on the structure or with a camera measuring a video of the motion of the surface, that is ODS data. So this is a time sweep, a time-based ODS from a camera video. And of course, there's millions of pixels in the video, and then in MEscope, we reduce it down to thousands of points on a grid that's behind the video. and then we display the frames of the video on top of the grid of points, but we have the same time and frequency data that we would get from a impact test. But this is what we call operating data. There may be impacting forces going on, but there's more like orders, forces that are, and we can see them in the spectrum. They're exciting the machine at specific frequencies that are multiples of the running speed. So there's the first order, and then here's the second order ODS, which is being dominated by a mode shape. Okay, let's get to the question. Mark, it's your turn.
Okay, we're going to open up the poll here, and you can answer which method you believe, or excuse me, if both methods are applied to a structure with 9 test points, do the 2 test methods yield the same modal information? So go ahead and pick one, yes or no. And based on that, I'm going to pick if you could type in either yes or no. If you want to type in the question box why you believe yes, why you believe no, and we'll pick one of those and read it out, and then we can kind of just go forward here with a little bit more discussion. Right now, the yeses are beating the no's, 62 to 40%. So we're still collecting more responses here, but
well, Mark, if
again,
I can interrupt, let me go back and explain the question a little bit.
Let's do that, yeah.
Because they've probably all voted based on the 2 pictures. These 2 tests are very common. They were taken with an impact hammer, a triaxial accelerometer. Now, triaxial just means there's 3 accelerometers all put together, and a 4-channel acquisition system or analyzer. So when we talk about a 2-channel, 4-channel analyzer, the data is being sampled and processed with signal processing simultaneously on all the channels. So we say the data is simultaneously acquired. So the first one we call a roving impact test. So the accelerometer is attached at point number 9 in the corner, and we go along and impact at point 1, and that will form 3 FRFs. Then we impact at point 2, and that will form 3 more FRFs. So if we impact at all 9 points, we'll end up with 27 FRFs. And then we talked a little bit about ODS, and now if we put the cursor on a peak, we can see the ODS, and if it's lightly damp structure, the ODS is going to be a good approximation of the mode shape. Okay, in the roving accelerometer test, we're going to move the accelerometer around and just impact at point 9. So again, this is using a impactor and a triaxial accelerometer and a 4-channel analyzer. But now the accelerometer is attached to point 1. We impact and collect 3 FRFs, or calculate 3 FRFs from that acquired data. Then we unglue the accelerometer, however it's attached. Many times if it's a steel structure, we use a magnet. If it's aluminum, we got to glue it down with hot glue or something like that. But let's move it to point 2 and impact again. So we collect or calculate 3 more FRFs. And if we do that with all 9 points, moving the accelerometer to each point, we end up with 27 FRFs. So the question is, if we've tested this structure with these 2 different methods, do they yield the same modal information? Mark, what's the result? Hello, Mark, are you there?
Yeah, can you hear? Can you see the results here? The quick poll. We've got
I'm not seeing it.
64%. You don't see it. 64% are saying yes, and 36% are saying no. Why you guys attendees are viewing poll results? I believe that they can all see that. Maybe you can't see that. So anyway, what we like to do here is if you voted yes, could you type in an answer why you believe it's yes? If you voted no, please type in the question dialog box there. Just type in your answer there. If you voted no, please type in an answer, and then we can kind of go forward here with some more discussion. Let me go ahead and hide that. I'll go back to the question here. That way you could, okay, we've got one person here. Let me just open up this. Bear with me. Okay, we've got Michael Mullen says reciprocity. Christian Gather says no. Christian, why do you believe no? Okay, here, because different direction.
Mark, can I answer the reciprocity question?
Okay, yeah.
That's a good answer, because reciprocity is a fancy word for saying the structure is symmetric. So it doesn't matter whether I hit it at 0.1 and measure its response at 0.9, or if I hit it at 0.9 and measure its response at 0.1. So that's what the student who answered reciprocity is using as his reason for saying that he answered yes, correct?
I believe so. I don't have his exact result here.
Okay.
Christian
Let me just say a little more about reciprocity.
Yeah.
That is an assumption that we make in modal testing. Now, are all structures symmetric in that way? Normally, we don't even test for it. We don't test to verify it. We just assume it. But for many structures, and certainly anything simple, this kind of looks like a flat plate here. We could go and do those two tests. We could impact at 1 and measure at 0.9, and then put the accelerometer over on 0.1 and impact at 9, and overlay the two measurements, the spectrum or the FRF. And if the reciprocity would say that I should get the same answer. Anyway, let's go ahead and.
Oh yeah, we got a lot more people that are responding now. Let me just go through some of these. Unfortunately, I don't know if you voted yes or no, so if you want to put that in the question, that would be very helpful. Christian Gather says, oh, no, because different direction. That was one. Chris Jens, the structure will still resonate regardless of where it is impacted. That was another response. Thomas Head says, linearity is the same if elastic. Let's see, I'm just going to read through some of these.
Sure, those are good.
Mass distribution of sensors in case 2. Jeffrey says 3 channels versus 1 versus DOFs.
Well, let's talk about the mass distribution answer.
Okay, good.
Now, again, we don't know whether these guys are voting yes or no. I would assume that's a no. Mass distribution is a problem because all the way back to the mass on the spring with the damper, we assume when we do a modal test, and especially an impact test, that the mass doesn't change. So that answer was assuming that the mass of the accelerometer was significant, in that on test number 2, as I move the mass along, or as I move the accelerometer along, its mass is going to change the overall mass of the test article. And that can be true. If I'm testing a very small thing, just some little medical device, tiny, that they put inside your heart or something, yeah, I can't put a large accelerometer on there and test it with test number 2, because it's called mass loading. It's going to change the mass between each of the 9 measurements. Okay, back to the, so that was a good answer. Let's go
Yeah,
ahead.
and he voted no.
Okay,
Yes,
for that reason, mass loading.
Yep, for mass loading.
The
Okay, here's
mass loading
Cassidy.
was a problem, but there's nothing in these two questions that will indicate that mass loading is a problem. If it's a tiny little Excel, and we can purchase tiny ones now that only weigh a few grams. So if I'm testing something small, I can put a tiny Excel on there and mass loading will not be an issue. Okay, let's go ahead to the next guy.
So we had one guy, Jeffrey said 3 channels versus 1 versus DOFs. And then Cassidy says, I say no because the way I understand it is that ODS is at a set frequency where the modal test excites all frequencies.
I'm not sure what he means by that. The impact hammer, now we didn't talk about the spectrum of the impact hammer, but the reason we use an impact hammer as opposed to a shaker with a sine wave excitation is the impact hammer has a spectrum that spans a lot of frequencies. So impact testing will excite a lot of resonances at once. And that's what we want. We want to excite as many resonances as we can with the impact hammer. And we'll even put different softness of tips on the hammer, and we have different size hammers, depending on whether we're trying to excite a big structure or a little one. And the reason we change the softness of the tip is to spread the energy over a larger spectrum and excite more modes or more natural frequencies. So I think that's what that answer was addressing, is the fact that the impactor is going to excite a lot of modes at once. And we saw in some of our FRFs, lots of peaks showing up. What else?
Let's see, we got one more in here before we, I don't want to go too long here. We got a long response here from David. Let me go ahead and read this and then we'll go from there.
Okay.
Modal test 1 yields FRF measurements from 3 rows of the FRF matrix. These 3 rows of FRFs will yield 3 estimates of the mode shapes in the Z direction and 3 directions at 0.9. In this test, the DOFs of the mode shapes are the same as the points and directions where the roving impact hammer hit the structure. Okay, modal test 2 yields FRF measurements from 1 column of the FRF matrix. This column of FRFs will yield 1 estimate of the mode shapes in 3 directions, X, Y, and Z, at each point. In this test, the DOFs of the mode shapes are the same as the points and directions of the roving accelerometer.
Okay, we're going to give him an A+. We'll give him an A+ on this exam. He went and read the app note, and he read the answer in the app note.
All right,
so his explanation was almost the same as these, although he put it in his own words, which is really good.
Very good.
So here's the answer. These are 2 different types of tests. The first test is called a multiple reference test. And we'll get into this whole issue of what do we mean by a single reference versus multiple reference test. And what are we talking about when we talk about rows and columns of the FRF matrix and all that mathematics. It will explain once we get there. We're going to do that in future webinars, so I invite you all to come back. We're going to schedule one for January, and then IMAC, the International Modal Analysis Conference, is in February. We're going to be there, so the next meeting will be in March. But anyway, let me just review some of that because David, I think his name was, he answered the question correctly. So the answer is no. The right answer is no. They give 2 different sets of data. One is a multiple reference set of data. However, the mode shapes in the first test are only going to show us motion in the Z direction or the vertical direction, normal to the plate where the impact hammer hit the plate. So, but we get three references. The reference is always the fixed accelerometer. The roving is, or in this case, the accelerometer. The roving is always the one that moves from one test to the next, one impact to the next. So this down here, the second test is the hammer is the reference and the accelerometer is roving. And if we go back to the answer here, as David explained, the second test measures a column of FRFs out of the FRF matrix of possible measurements we can make on this structure. And the mode shapes are going to show us motion in X, Y, and Z directions. And even if we put a cursor on one of the resonance peaks, the ODS is going to show us motion at 3 UOFs at each point, X, Y, and Z motion at each point. So, good answer, good participation. Let's move on. I want to introduce, now this is our price list of the MEscope packages, and you can see that the way we've structured all these packages, and if you just read through here quickly, they all start out with our base package called Visual ODS. That was the first package we came out with back in 1991. So Vibrant is going into our 32nd year of business, doing the same thing. We start out with an ODS package where you just put the cursor on a peak, and that's many times for lightly damped structures a good approximation of the mode shape. Then Visual ODS Pro adds signal processing, and there's a lot of details there. You can see the price goes up a little bit. Rapid Test, which is what we're going to use next time in our next webinar in January, that includes ODS Pro plus an acquisition option. So that, well, we'll talk about that in a minute. Then our modal package is an ODS Pro plus our modal analysis option. So this is a food chain, and then Modal Pro adds our advanced modal analysis option to our modal package. And then SDM, which is structural dynamics modification. We have two different packages, one that adds SDM to our modal package, the other adds it to our Modal Pro package. Finally, STN is everything. It adds finite element analysis, video processing to the SDM Pro. So just wanted to show you that, and then we'll come back. But the two things that are in our rapid test package are unique to MEscope, and we're going to talk about rapid impact in January, and then in March we're going to talk about a TRN chain, which is called a transmissibility chain. And those two are unique in the sense that rapid impact allows me to move the hammer and accelerometer along together. So I don't need to run a long wire. If I'm testing a piping system or a bridge, I don't need to run a wire from one end to the other because one of them is a reference and the other is roving. With rapid impact, we can move both of them. They can both be roving together. And TRN chain is the same thing, only there we're just measuring something called a transmissibility, which is a ratio of two accelerometers. So we'll get into all that in the future. Different ways of testing big structures where I don't have to run wires, half a mile from one place to the next. Here's our video processing packages. One is, again, Visual ODS, and it adds video processing to the ODS package, and then the second one adds video processing to the ODS Pro package. So again, these are all built on Visual ODS. Here's just kind of a pick list showing, and these are the different options. They have different numbers. We won't go into all of them. right now. This is a little description of our multi-channel acquisition. So MEscope we're just a software company. We don't sell hardware. We don't have our own acquisition hardware, but we do interface MEscope to a number of different third-party acquisition hardware. Now, again, as in the first video, what we really want are the digitized time waveforms simultaneously acquired on multiple channels. Brian Schwartz is with me here. Brian, do you want to say more about this?
Okay. Yeah, I mean, first of all, we work with all of the data acquisition hardware available today for importing data, bringing data into MEscope. We spend a lot of time making sure that you can always get your data from whoever's analyzer, whoever's data system you're using into MEscope. But we also have the capability of controlling several different manufacturers' front ends. You know, and some of these are very inexpensive, such as the Modal Shop. They have a little 2-channel analyzer through their digitucer group called the 45B39. It's basically 2 channels, supports ICP sensors, and it's basically a digital sound card, but it's less than $1,000. You know, other less expensive solutions would be like from Data Translations, National Instruments, Roga Instruments is another less expensive. They're over in Europe. Then they typically provide less in the way of any kind of front-end capability for the cheaper solutions. You know, but then you get into a lot of these other higher-end solutions. Alta does a lot of work in machinery analysis. Data Physics does both testing and vibration control. MEcalc has been supplying the hardware for MBBM vibroacoustics, but now they've started also marketing it on their own. Onosoki is very popular over in Japan. Oros is from France, but they sell worldwide. Sinus is another European hardware manufacturer out of Germany.
Good. Well, thank you, Brian. That's a good summary. Mark, I think we're done unless there's some questions that we might want to answer to wrap it up.
If anybody has any questions, we got a couple minutes here. We could answer a couple questions quickly if anybody has some lasting questions. Obviously, we can certainly answer some questions too if you want to email us. Easiest way to get a hold of us is just at sales@vibetech.com, and we can get those questions answered for you offline. In addition, I did want to mention some additional modal testing, or excuse me, modal training is done by our partner at Navcon Engineering. They have a hands-on modal testing analysis training seminar conducted out in Southern California. They got 4 different trainings coming up here in 2023, February, May, August, and November. These are very, very well attended and probably one of our some of our best training programs come out of those trainings conducted there at NavCon. But you can get more information at NavCom, NavCom, and excuse NavCon, NavCon, excuse me, NavCon Engineering. Go ahead and take a look at their training offerings. Also, you can go to our website, and if you click on the very top, you can click under Learning, and you can also find out more information there directly from our website as well. We have all of those 4-day hands-on training sessions listed under there. So I encourage you, if you want to get some more modal testing, to check them out at NavCom. They are excellent. And I believe Jim was on our webinar today, in fact. So thank you, Jim. I know you put that you were a beginner. You are far from a beginner at this. So. No questions at that. Oh, wait, no. Yeah, there he is. I don't have any additional questions at this time. Yeah, do want to encourage you to take a look at our website again and our YouTube site as well to review not only this webinar, but all of our past webinars as well. You should be getting an email, like I said, a recording of this webinar here in a day or so from the GoToMeeting folks. Anything else, you guys, on your end?
I might just advertise our app notes. This is application note 5. So if you own MEscope, you can go and read these app notes, and most of them have MEscope projects associated with them. And they have something that we didn't talk about, but MEscope has scripting built into it, and it comes with every package. Now that's programming, and I know most engineers don't like to program anything. They just want to solve their problems. But if you go to the app note and download the project associated with it, now not all app notes have one, but many of them do. The app note has hotkeys, and a hotkey, if you press a hotkey, that will execute a script, and it will take you through the steps of the app note. So you either get tired of reading the app note, which is a lot of details, or not sure how to run MEscope. But if you just want a refresher course, go and, again, this is to people who already own MEscope, go and look at some of these app notes. I think we've got over 50 of them out there. So, and we're continually working on those. I'm going to use another app note in January, actually a couple of them. We've got 2 of them on rapid impact testing, one with a 2-channel analyzer and one with a 4-channel. And we'll go through the details of that. Anyway, enough said.
Good stuff. We'll go ahead and wrap it up there. We wish all of you a very Merry Christmas and a Happy New Year, and